This is either genius or stupidity. Where are you going to put your money down? It's stupidity, isn't it? Fine, I guess we'll see. Hello Internet, my name is Quinn, and this is Blondihacks. I'm back on the Pennsylvania A3 switcher this week, and I'm continuing the journey towards a rolling chassis for the tender. So, let's go. With the wheel sets done, it's time to work on the trucks. Now, I believe the Brits would call this a bogie, which is probably a better word for it. It's the assembly that holds the suspension and the axles and the wheels together. Here in North America, we call it a truck, which is perhaps unfortunate because we also call this a truck and this a truck and this a truck, and well, sometimes it's a verb. So, we like to overload words over here. I'm going to start with the journal boxes. They look like this. It's basically a box that holds the wheel bearings on a typical railroad car of this era. Now, these ones are mostly decorative other than being structural. However, on the real thing, they would be boxes that you could use to access the bearings for greasing or oiling. They might have an oil reservoir in them, that sort of thing. I've got this brass square bar for the purpose, and we need 8 of them, of course. I'm going to say it'll be nice when the tender is done and I can stop making 8 of everything, but we're still in that world, so here we go. I'm going to rough cut 8 of these pieces on the bandsaw, and then they will need to be machined down to an accurate length over here on the milling machine. Since I am still in the land of making 8 of everything, I'm going to be doing a lot of this sort of thing. I've got an end stop set, so after machining one end of the first piece, then I machine the second end of that first piece down to an accurate dimension. Once this piece is machined down to the exact right dimension, I can just zero the DRO right there and then run all the other pieces through. So I only have to measure the first one. I have to sneak up on the dimension and take my time on the first piece, but then the other 7 go very, very quickly because it's just a case of facing one side, put that side on the end stop, flip it around, and machine the other side down to 0. Next is the bore for the bearing. It's a shallow blind hole, and this goes on the center of one of the long sides. So to mark the center of each of the long sides, I've got my height gauge set to half the distance of the short side, and I mark one axis of the center line on all 8 parts. Once again, trying to minimize tool and instrumentation changes. Then I set the height gauge to half the long distance and run that through all 8 parts. This is a quick way to mark the center of all 8 parts. I really enjoy surface plate work, and I love any excuse to do it. To punch those center marks, I'm going to use an optical center punch. This is something I've had in my drawer for a long time. A viewer donated it to me, but I haven't used it a whole lot, so I thought it would be fun to give it a whirl here. The way these work is there's a collar that holds an optical loop, as you see there, and inside that loop is a crosshair. And the idea is you put that crosshair on the scribe lines, the center of the scribe lines that you've marked. Here you can see what that looks like inside the lens. The white cross is the scribed marks on the piece, and the black cross is part of the loop. So you line up the black cross on the white cross. Essentially, you fill in the white lines with the black lines, and that loop is now perfectly centered on your scribe marks. Then, trying not to move the collar, you carefully remove the loop. This is easier on ferrous parts because the collar is magnetic. Then you insert this little transfer punch that the kit comes with, give that a tap, and now your center is marked. This is intentionally a light-duty tap, so it's just a starting point, but it should be very, very accurate. It's trading accuracy for power. Then you deepen that punch with something like a spring-loaded center punch, and now that's ready to use. So I ran through all 8 parts to find the center that way, and now I can put them up in the lathe and get ready to do the bore. Now I need that center punch on the center axis of the lathe. For that, I've got my dead center, which I put in the punch mark. I hold the back of it with my live center, and then I can dial in the dead center just as though it was a round piece of stock in the forejaw. This is a simple technique for centering a punch mark that works extremely well. You'll see as it spins up here how well that punch mark is centered. Now I can center drill and then drill out this counter bore that we're going to be forming. Now for the drilling, which is to remove the bulk of the material and make room for the boring bar, I'm using a very special drill. This is a DeWalt Pilot Point drill, which has a mostly square grind on the end. These things are great for starting flat-bottomed blind holes because they have that square grind on them and they really save you a lot of work with the boring bar. Drilling depth is super crucial here, so you see me using an indicator on the tailstock quill to make sure I get my depth really accurate. And then it's just a matter of coming in with the boring bar and cleaning up that bore, bringing it to dimension. We also gain all of our concentricity back that we may have lost with the drill by doing this. Tolerance is very tight on these. They have to be accurate, so I'm using gauge pins. I have a couple of sizes leading up to the dimension that I want, and I'm taking light cuts with the boring bar and checking with my series of gauge pins, working my way up to the final dimension until I get a nice, comfortable fit on the dimension that I want. And then, of course, as you know by now, I then have to do this 7 more times. There's the 8 journal boxes brought to this point, and now we're going to be spending some quality time over on the milling machine. The next features to do are grooves top and bottom for holding the arch bars. That's part of the structure of the truck. I'm going to do this on the mill, of course. I've edge found on the back edge only. That's the only reference I need. Referencing from the back of the part is a conscious choice because that's the fixed jaw of the vise then that you're referencing effectively, and that will ensure maximum repeatability between parts. Again, when you're making 8 of something, that does matter. And I've got an end stop, of course, although for this particular feature, the end stop isn't strictly necessary. And I run through all 8 parts once again, putting a little groove, in this case, on both ends of the part, because the structure of the truck attaches top and bottom to these journal boxes. So I have to do this 16 times. Those 2 grooves adds 16 edges to each part, so now I get to spend some quality time with a safe edge needle file to deburr all those edges. And this is important because if you've got burrs everywhere on your parts, then on the next series of operations, you're going to have burrs getting trapped between vise jaws and up against end stops and so on, and the accuracy and repeatability of your subsequent fixtures and setups is going to go to heck in a handbasket. Next up is a whole bunch of tiny bolt holes to attach the journal boxes to the structure of the truck. We need 4 of these per journal box. They have to be accurately depthed because you don't want to break into the journal bores. And because the holes are shallow, we need all the threads that we can get, and so each of these holes requires taper tapping and bottom tapping. So that's 64 tapping operations that we have to look forward to. Once again, I'll be glad when I'm not making 8 of everything. For a process like this, you really want to be thinking about efficiency. So in my case, I'm doing the center drilling and tap drilling for one side of one part first. Then I flip the part over, do the same thing on the other side of the same part. Then I do all 8 parts that way. Then I come back in and do all of the tapping. This strikes a balance between tool changes and part changes. Part changes take some amount of time and tool changes take some amount of time, and you need to decide which of which you want to do the most of. In this case, switching drills is fairly quick because I don't have to move the head to do that for these 2 drills that I'm using, whereas switching to the tap is quite time consuming because I have to move the head up and down switching between tapping and drilling. So that's the balance that I struck here. And note that the end stop on the vise is crucial to this because it means I can swap the parts as much as I want and not lose any accuracy. A simple vise end stop like you see me using there is an extremely powerful tool for mass production and repeatability. That vise stop is shop made. I have a video on making that if you're interested in making one yourself. On now to the angled features. For this I'm going to need a couple of fixtures. I've got this stuff here. This is called Mix 6. It's basically aluminum gauge plate. It's Blanchard ground on both sides to be very flat and a very accurate thickness. Making fixture plates and such is exactly what it's for, and it's super nice stuff to work with. I absolutely love it. I marked and bandsaw cut a piece of it, and I'm going to clean up all of the edges. Because the front and back are already ground parallel and flat, it really saves you a lot of time because you can do a setup like this where you simply mill all 4 edges and you don't have to do any trickery with copper wire or so on like you normally do when you're squaring up stock. It really saves you a lot of time. So you can square up all of the edges of your soon-to-be fixture plate, and everything's going to be accurate, and you can use it for references for implementing that fixture. Kozo helpfully provides the dimensions for the angle required for this fixture as a rise and run, or slope if you will, so that's easy to transfer on to the piece with layout. Now to get a parallel cut at an angle that follows that line, this is my favorite trick for doing that. Put a parallel on your vice jaw, line up the scribe line with the parallel, remove the parallel, and now you can mill down to that line without hitting your vice jaws. This is more than enough accuracy. We don't have to get out the sign bar or anything to set up this angle because these are just decorative faces on the fronts of the journal boxes. That little notch will hold the pieces at the correct angle for the larger face. Then for the smaller angled face underneath, I need another notch, and that's at 45 degrees. So I've got one of my little 45-degree angle squares in the vise that I use to set the piece at this angle. Then it's just a case of side milling my way in until I've got a depth for that angle that looks like it'll hold the block comfortably. I need to make sure that I've got enough meat in the fixture that I'm not landing on the middle of one of my grooves or something like that. I have to have a secure fit that will hold the piece. One last detail that I think often gets overlooked in fixtures like this is an undercut on those inside corners. Anytime you have an inside corner in a fixture, you have to undercut it. No matter how sharp a cutting tool is, there's always a nose radius on it, so that means you're going to end up with a fillet in that inside corner. It might be too small to see, but that fillet is always there. And that fillet will prevent parts from seating properly down in that inside corner. So with that undercut, as you see here, now the part is guaranteed to be sitting perfectly down in the corner on all sides. Only takes a second to do that, and it absolutely transforms the security and the repeatability of a fixture like this. Now it's very quick and easy to tap each piece down into the fixture, and it's guaranteed to be held at the correct angle for milling flat to create the angled surface. You saw me using a reference for the end of the vice jaw to set the position of this fixture horizontally. That actually isn't important, that's just a force of habit. I always do that just in case it matters, but for this fixture it doesn't matter because the end of the part is held as well by the fixture. If you're using just a plain angle block, then horizontal position of the part does matter because milling to the same depth won't create the same feature if the angle block isn't sitting in the same horizontal position. As always, I'm sneaking up on the dimensions for the first feature, and then I'll have the 0 set on my DRO for all the rest, and I won't have to do all this measuring. The drawing gives me 2 dimensions that I'm aiming for: the thickness of the little edge and the width of the unmachined remaining surface. First one done, and everything looks good, so I 0 my DRO there and run through the other 7. Next, I run through all 8 again using the same method, this time on the other notch in my fixture to add the smaller 45-degree chamfer on the bottom of each of the journal boxes. Easy peasy. 3 of the surfaces are still unmachined. They remain the factory stock surface, and those surfaces never look that great, so a little time with the Scotch-Brite wheel shines them up a bit. There's all 8 pieces there. They're looking pretty decent. I do have some jaw marks from the chuck on a couple of sides, but I managed to get most of them out with the Scotch-Brite wheel, and they're going to be painted, so I might fill those as well. On to the bearings. I have some phosphor bronze for this. These bearings are deceptively cool. They're not just basic bushings, they're actually barrel-shaped, and you'll see why at the end. It's a very interesting design. I'm still the mayor of the land of 8, so more mass production. I'm going to start by roughing in each bearing as a simple cylinder, and we'll add the tricky barrel-shaped features later. Per usual, the first one is a lot of sneaking up on it, making sure the dimensions are exactly right. The tolerances again on this are very tight. Has to be a good sliding fit on the journal box. And then of course the hole down the center needs to be a very close running fit on the axles. But some basic drilling and reaming gets that done. Once I've proofed with some test fitting on the mating parts that I know my dimensions are good and my choice of operations is sound, then I can once again run through the other 7. And again, I can use the DRO values to repeat all 8 of these without needing to measure anything after the first one. I parted each one off long, and then I was supposed to go back and face each one down to length in a new fixture. However, I forgot to do that, but more on that in a second. Then the remaining features are done on a mandrel, again for easy repetition. I need a taper on both sides of every bearing, which would be a lot of compound setups. So a mandrel will save me a ton of work, as you'll see. I turn that down to size, I put a thread on the end, and then once the thread is on the end, then I turn down the reference area to the exact size required for a very, very close fit on each of the bearings. To secure those, I found this weird little thumb screw in my hardware bin. I have no idea what it's from, but it happens to have the right thread on it, and it will be a handy way to secure each of these bearings in place. The diameter of it is a little bit large. I need it to be smaller than the final bearing will be, so I just put in a left-hand turning tool and turned down the body of this thumb screw to size. You could also use a very small nut or something along those lines, but I found this thing in the bin, so might as well use it. Now, as you can see, it's slightly smaller in diameter than the bearing, and I can turn the taper on the end. And I mean, if I cut into that nut there a little bit, it's fine. I mean, that thing can be considered sacrificial. To create the barrel shape, each end of the bearing needs to be tapered to 3 degrees. So with a protractor, I'm setting my compound at 3 degrees, and I'm going to blue up each part as I go, which is going to help me get the dimensions accurate for where the taper starts and ends. That's a tricky thing to do with tapers. Using my calipers to make a light mark in the bluing, I'm not scribing the material here, just marking the blue to give me the high end of the taper. And then I'm going to determine where that ends up being on the DRO by trial and error. This is very similar to how the wheels were done, if you may recall. I do light cuts from left to right until I land right on my line, and then for all remaining cuts I will know where the DRO value is for the start of that taper. Positioning tapers accurately on a part, especially for very, very small parts like this, can be very difficult. But this is a simple method to get very good accuracy, certainly accurate enough for what we're doing here. For each pass, I start by zeroing the DRO for the cross slide and the carriage, and then I've zeroed the compound hand wheel at that position as well, so that when I have the accurate taper right up to my line, then I know with everything zeroed, it's the correct place to start. This is the moment where I realized I'd forgotten to face these parts down to length first, so my reference line for that taper was incorrect. That's okay though, we haven't scrapped that part, as you'll see. So I'm just going to switch gears, I'm going to pull out the collet chuck, but leave my mandrel in it, so I don't lose the concentricity on that mandrel. Bring in my 3-jaw chuck, and I'm going to turn a quick fixture to hold all of the bearings to face them down to length. I'm not losing any time here because I was going to have to make this fixture anyway to do the facing. I start by drilling out a rough dimension for the mandrel, and then I bore it out to final dimension to get concentricity and to create a little shelf in the back of the bore. It's going to give me a depth reference for these parts, as well as holding them concentric to the lathe. Once again, like on the journal bores, I'm working to a set of gauge pins to get that dimension set. Now the bearing is a very, very close fit in there. I can just press that bearing in. That's what I want. Very close fit is going to ensure concentricity of the fixture. Now I do a slit down the center of the fixture with a fret saw. This does not have to be accurate, hence the ham-fisted sawing. This goes all the way down basically to the depth of the drilling that I did. The longer these slots are, the better, because they'll give it more flexibility. I think you see where this is going now. I'm basically making a 5C collet from scratch. Now to close that collet, I'm going to use a precision Starrett machinist's hose clamp, or a farmer's collet closer if you like. And that works way better than you might think it would. That works extremely well, as you can see. That's running very, very concentrically, and this very tiny part that's a very strange dimension is held perfectly accurately. And the great thing about this fixture is it repeats incredibly well on depth and concentricity. So it's very, very quick to run through all 8 parts, and I've got the depth set on the DRO for the final length of each part. I don't have to measure a single thing, and I was able to face down all 8 parts very, very fast. So strong recommend for this type of quick and dirty emergency collet. As before, I left that fixture in the chuck just in case I need it again. I won't lose my concentricity. Now I can switch back to the collet chuck, which has my mandrel in it, and as you can see, I have lost no concentricity from that little detour. Now I can recut the taper on that first bearing that I did wrong. Because the bearing was overly long, the error worked in my favor, and I didn't actually scrap the part. I can just recut the taper using the same DRO values, mind you, because my reference edge is still the same. The reference edge against the back of the mandrel was correct. So my DRO values are still correct. I recut that initial taper. Now I can flip the part around and cut the second taper, and it will be perfectly symmetrical with the first one. And I can run through all 8 bearings this way very, very quickly. And the great thing about this is I get both tapers on both sides of every bearing without ever touching my compound. I set that 3-degree angle once, and all 16 angles are guaranteed to be identical. If I did my job right, you'll see a 20 thou wide band in the middle of blue that remains. That little band in the center is crucial because that's the running diameter of the bearing. That's what holds it in place in the journal box. So we need that, but the barrel shape on either side is what allows the axles to tilt. That is why we've made them barrel shaped. You'll see how this all goes together in a sec. Mea culpa time. I actually made all those journal boxes to this point twice because I put the counterbore in the end instead of the long side, and I had to make 3 extras because 3 of those incorrect bores were oversized. So I scrapped 11 parts getting to this point. Yeah, I didn't show you all that because it wasn't an interesting set of errors. Also, that super cool mandrel, I made that twice as well because the drill cut oversized the first time and I blew that dimension. So just so you know, I don't show you every tiny thing that goes wrong, but machining teaches patience, and don't be discouraged if you have to scrap parts or even mandrels sometimes. Just keep working through it and you'll get better at this stuff. Final assembly time. Let's see how this all goes together. You'll get to see why the bearings are barrel shaped now. The bearing goes on the end of the axle like so, and then that assembly fits into the journal box. The journal box is what attaches everything to the frame of the truck, the arch bar frame. And now, as you can see, the journal boxes have tilt in them. That allows the axles to tilt to follow the track. So this is a crucial part of the suspension system of a railway car, that ability for the bearings to tilt. It's all about suspension. Rails are never perfect, and if you can't follow the rails like that, then you will derail. Quick mock-up then of all 8 of them, and you'll see kind of how things are going to look. You can imagine those pairs of journal boxes joined with truck frames, and soon they will be trucks. You can see them kind of sitting in an angle as they sag under their own weight from that tilting action, but of course eventually they'll be joined to trucks, and so they'll be sitting on the center band of the barrel shape that you saw earlier. This looks fine, I guess. This is certainly what they're supposed to look like, but those large flat surfaces on the outsides of the journal boxes were nagging at me, and I slept on it for a couple of days, and then I had an idea for a last-minute addition to give these things a little more detail, make them look a little more interesting. The original purpose of a journal box, of course, is to give access to the bearings that are inside. So there would prototypically be a hatch or some other way to access the bearings inside for maintenance and lubrication. So I set them up in the mill once more and did a little bit of work with an engraving bit, and this is the result. I have the sort of impression of a little hatch or a door of some sort on the front of each journal box. I think this is a nice addition. What do you think? Well, there you go. That is all the time I have for you this week. I hope you enjoyed watching the fascinating process of making journal boxes and bearings for a railroad car. Thanks to all my patrons for making all of this content possible, and I will see you next time.